Good morning. Today we're going to talk about free fall, which is just our kinematics in the y direction. So we're going to take what we already know, we're going to tweak it just a little bit, and we will be able to solve problems using the UAM equations in the y direction. So, free fall. Free fall refers to the motion determined by gravity. So this force of gravity, which we'll talk about later in the course, is actually going to cause things to accelerate downward. So Galileo is the first one really to prove that in the absence of air resistance, all objects will accelerate at the same rate, regardless of their mass. So we're going to take a quick look at an Edpuzzle.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel. So this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Okay, so make your prediction.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball.
And why do you think the feathers took longer to fall? Most people used to think that the feathers were lighter than the bowling ball, and that is why. But it's really because of
air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
make your prediction.
Look at
exact. They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down.
Hopefully you will guess this correctly, and if you don't, it's not a big deal, but just remember that it is the force of gravity.
Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all.
This is Einstein's theory.
He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
So that last part was Einstein's theory pertaining to relativity, so we are not getting into that in this course. So let's go back to what we are doing. Okay, so you can do this little experiment at home if you have just a rubber ball, whether lacrosse ball, field hockey ball, basketball, and a sheet of paper. You can drop them at the same time, and you'll see that the sheet of paper will waft through the air and reach the ground much later than the ball. However, if you crumple up the piece of paper and you let them go, they will hit the ground at the same time. Again, it's because of the size rather than the mass. Okay, so here's an idea. Most people think free fall. They think objects are always moving downward, and that's not the case. Any object that is free from all other forces except for the force of gravity are considered to be in free fall. So even when an object is moving upward, there is still an acceleration on that object. So it's always pointed downward, this acceleration, and this acceleration is always due to that force of gravity. So it doesn't matter if you toss something up, if you drop something, or if you throw something downward. All of those situations are considered free fall. Okay, so for objects on Earth, our acceleration due to gravity is this number here, 9.8. You might see it as 9.81. You might even see it sometimes rounded up to 10 just to give a rough estimate. But on Earth, 9.81 meters per second squared. What this is, hopefully you recognize the units, that is in units for acceleration. So what we're going to do is we're going to give this special acceleration the lowercase g, so little g. Little g is always 9.8 meters per second squared. Now you can see I just thought that this was interesting, so I kept it in here, but we won't really be doing problems associated with this. However, little g does vary a little bit by location, and then it will also vary a little bit with altitude. But for our class, we're going to keep it as acceleration on Earth is 9.8 meters per second squared. Now we also know that it's a vector, and we know that it's always pointed downward. And so for our class, little g will always be negative. So we can always have a negative in there because we're always going to choose down as negative and up as positive. Okay, so that should definitely go in your notebook as well. All right, so we can use our UAM equations, and the only things we're going to do is we're going to substitute in for A, we're going to use negative little g, and then for x we're going to use y. Okay, so you might want to take a screenshot of this. These are the ones that you have already, and these are for the vertical direction. So these are for the horizontal, these are for the vertical. And you can see that they're exactly the same. The only difference is we put in a G here and a delta Y here. Those are the only differences. Now, one thing I do have to note is that when we're in free fall and we're talking about final velocity right before it hits the ground, some of your problems will say, hey, what's the speed when it hits the ground? We're talking about the instant right before. So we're not saying, hey, it hit the ground, it stopped moving, it's 0. We're talking about the instant right before it hits the ground. So keep that in mind. Okay, so I have another little intro video.
Skydivers and wingsuit flyers may call what they do free falling, but as you may have noticed by now, in physics, words mean something a little more specific. So let's explore what free fall is all about in this segment of Physics in Motion. Free fall is what an object does when it is under the influence of only one force, gravity. We have to go way back in history to get a handle on why this matters, but we'll keep it short. For thousands of years, scientists thought that how fast something fell depended on how heavy it was. Seemed only logical. But in the 16th century, one of the all-time Science Hall of Fame geniuses, Galileo, had an idea. He suspected that all objects, regardless of their mass, fell at the same rate of acceleration. If he were to take two objects, one light and the other heavy, and drop them from a height, they would both hit the ground at the same time. This showed that acceleration is independent of mass. Let's go try this ourselves. So between this watermelon and this cantaloupe, which do you think will hit the ground first? Both hit at the same time. The watermelon made a bigger mess, but as far as acceleration goes, we verified Galileo's point. It even works on the moon. Take a look at this clip from Apollo 15. The gravity on the moon, even though it's less than that of Earth, still made the feather and hammer drop at the same rate of acceleration. Gravity, in fact, is one of the most important forces in the universe. So back to the 16th century. When people realized that objects behaved this way, it was a major turning point in understanding how the universe works and being able to predict how things will move. Galileo, using the instruments available to him, measured the acceleration that was due to gravity on Earth, no matter what the object, at about 10 meters per second squared. We now know it is 9.8 meters per second squared near the surface of the Earth, so he wasn't far off, which is impressive considering he used his heart rate as a timer. That is the constant rate on Earth that the force of gravity accelerates everything. All objects, regardless of their mass, fall at the same rate, 9.8 meters per second squared. But, you say, what about air resistance? And you're right. But let's put other factors aside for right now, since we're only concerned with how things work in free fall. We'll get to those in another video. Now, let's look at a free fall problem together. Let's say that we throw a ball upwards. What is the ball's maximum height? And why is that a free fall problem? Because technically, an object is in free fall even when moving upwards or instantaneously at rest at the top of its motion. Because, remember, free fall means that gravity is the only force acting on an object. We can use some of the variables we know to plug into an equation to solve the problem. The origin is the place the ball left our hand, and the positive direction is up. Let's say I throw the ball at 10 meters per second up in the positive direction.
Okay, so let's just look at our strategy. What we're going to do is we're going to start off each problem and just remind ourselves that up is positive and down is negative. And you'll see why a little bit later. We're going to write out our kinematic equations. And if you see, I can automatically fill in A. I know that it's negative g, which is negative 9.8 meters per second squared. The negative, again, just means that it's pointed downward. G is just the size of the acceleration. It's going to speed up or slow things down by a rate of 9.8 meters per second every second. And now, let's fill in some other things. He wants to know how high will this ball go if I throw it upward at 10 meters per second. So you might be thinking, you know what, I don't have enough information. And right now you don't. So we have to learn a couple of key types of problems. If you throw something up, it's going to reach a max height. And if you think about it, it's going to slow down all the way until it reaches this maximum height, and then we know it's going to come back down. So what's its velocity up here? Once it reaches its max height, its velocity up here is going to be 0. So I know that third piece of information. So that's one type of problem when they ask for the maximum height or how high it goes or anything. If they give you that max height and they want to know how long it took, anything like that, whenever you think of max height, think its final velocity is equal to 0 right at that point. Now, a common, very, very, very common misconception is that the acceleration at this point is also 0. However, the acceleration is due to the force of gravity. The force of gravity is always acting, so the acceleration due to gravity is always acting, and it's negative 9.8 meters per second squared. In fact, the acceleration along this whole entire path is exactly the same. It is always negative 9.8 meters per second squared everywhere. And we'll look at another problem and really dissect that. But for now, make sure you have that somewhere in your notebook so you can refer to it. Once we get our information, we can just go ahead and we can pick out our equation from our kinematics list. And we want to choose the one that does not have t. So it's our final velocity squared is equal to our initial velocity squared plus 2g delta y. Okay? So you can go ahead, and if you accidentally put it in the old way, it's fine as long as you know how these correspond in those equations. You're totally fine. So I wouldn't take off points for writing it with x, delta x, and a. But your final velocity is 0. Your initial was 10 squared plus 2. Don't forget the negative 9.8. And we're solving for the displacement in the y direction. All right, so at this point you're just at algebra. So we got 100 and then plus negative 4.9 delta y, and then take the 100 over, and then your delta y turns out to be 5.1 meters. Okay, so that means if you throw a ball or anything really up in the air at 10 meters per second, that it's going to travel 5.1 meters. It's positive, so we know that it works out and that it's moving upward and our displacement is upward. All right, let's keep going. All right, so how fast must a ball be thrown upward to reach a height of 12 meters? Same type of problem. I highly suggest you just pause the video and try it yourself. I'll get you started though. We know that up is positive, down is negative. All right, so pause the video and come back once you've tried. Okay, so you can assume that this is the maximum height is 12 meters, and we fill in our variables. We want to know how fast you have to throw it. Here's my final velocity. The displacement is 12 meters from where it started, and the acceleration due to gravity is always negative 9.8 meters per second squared. And here we go. We get our final velocity is our initial velocity squared plus 2g delta y. That's a 0 again. We're solving for initial velocity plus 2 and then negative 9.8, and our displacement is a positive 12 because it went up. So if we do this math, and then we bring that over to the other side and we get 235.2 equals initial velocity squared. So you got to take the square root of both sides and you end up with an initial velocity of 15.3 meters per second. Now remember, when you take a square root, it's plus or minus, but we know that we threw the ball upward, so we're going to choose positive for our answer. And you'll see how that comes into play in our next example. Okay, so here's a totally different type of problem. This says that you're going to drop something off a cliff. So this is another type of problem. If it starts from rest, that means it's dropped. So right off the bat, we're going to remind ourselves that this is positive and down is negative. So this ball is going to travel from here downward. Keep that in mind. So the key here was dropped indicates an initial velocity 0. VF is going to be right before it hits the ground. Delta Y. Now, here's another tricky thing. If it's moving from a higher point to a lower point, that means that my displacement, my delta Y, is actually negative. So this cliff is 490 meters tall, right? But my displacement, where the ball went, was negative 490 meters. My acceleration is always, and we want to find out how long, right? Okay, so nice. So at this point, we get to just choose one of these kinematic equations, try and find one that doesn't have VF in it. Again, it might be trial and error until you do enough of them, but I will let you know delta Y is equal to initial velocity times time plus 1/2 gt squared. This is great because my initial velocity is 0 and this guy just goes away. And I'm left with delta Y equals 1/2 gt squared. Now let's start plugging my numbers in. I'm going to come down here because I ran out of room here. So don't forget your negative. That's a real easy mistake to make. It's negative 490 because it went down, and then 1/2, and then negative 9.8, and then t squared. So again, at this point it's just algebra. And if you divide both sides by negative 4.9, you get a nice, easy t squared is equal to 100. So my t is equal to 10 seconds. It'll take 10 seconds for that stone to start from 0 velocity, go all the way down 490 meters. All right, how about another type of problem? We get a bullet is fired vertically actually it's a cannonball, is fired vertically upward and returns to its starting height in 20 seconds. Find the height that it reaches. So here, the reason we did this problem is for symmetry. Free fall problems are really neat. They're very, very symmetrical. So we go, it's moving upward, it gets to its maximum height, its velocity is 0, and then it returns here, right? If it returns right to where it started, there's a whole lot of symmetry going on. Let's look at it. My initial velocity is a positive v, yes? And then it's going to slow down, slow down, slow down, get to 0. And then it's going to come back and speed up, speed up, speed up, speed up. This velocity is going to be the same exact value, but just a different direction. So for example, if I were to send it up with a velocity of 10 meters per second, that's 10 meters per second in the positive direction. It slows down till it gets to 0, and then it's going to speed up until it gets to negative 10 meters per second. And again, that negative just indicates the direction that it's moving. Remember that your acceleration is negative 9.8. On the way up, remember that your acceleration is negative 9.8 even at the top. And then remember on the way down, my acceleration is negative 9.8 as well. And if you recall from the last section, if my signs are different, if I have a plus and a minus, or a minus and a plus, then that means that it's slowing down in that direction. And if those signs are the same, then it means it's speeding up in that direction. Remember, the velocity tells you the direction it's going. This is going in the positive direction. This is going in the negative direction. And then the acceleration tells you whether or not you're slowing down or speeding up. So it should make sense that when you throw something up, it's going to slow down. It's finally going to reach its maximum height. My velocity is going to be 0 for just a split second, and then it's going to return back down. What comes up must come down, right? So, knowing that, let's take it one step further with one more key piece of information. The time up and the time down are equal. So it's going to take the same amount of time to go up as it does to come back down, regardless of the object. So time up is going to be equal to time down. That's really important, and that really needs to go in your notebook because it's going to come in handy. In fact, it's going to come in handy right now because we're going to remind ourselves that up is positive, down is negative. Then we're going to start our kinematics list. Initial velocity, final velocity, displacement, acceleration we know is negative little g, which is negative 9.8. Make sure you can tell that's a negative. And then time. So let's fill out what they give us. A bullet is fired vertically upward and returns to its starting height in 20 seconds. Find the height it reaches. Well, let's look here. We can get some information, right? What do I know? I don't know anything about initial velocity. I do know, though, that the maximum height, let's look at it that way. We could say my final velocity is going to be 0. We want to know this, so I need one more piece of information. Well, I know that the total trip up and down takes 20, so half of that trip is to get up here. So that would mean that half that time would be 10 seconds. So it takes 10 seconds for that bullet to reach its maximum height. Then it will take 10 seconds to come back down. So we can look at it this way. And the thing is, when you look at your equations, you have to have initial velocity somewhere. So this is going to be a two-step type of problem. And I'm going to get rid of all of this real quick so I have room to write. So first thing you want to do is you want to find your initial velocity. So find an equation. You might want to pause for a moment, find that equation to find initial velocity, and then from there you're going to find your displacement. Okay? So go ahead, pause the video and see if you can find your initial velocity. Alright, so I'm going to choose this one because it does look like the most simple. My final velocity is 0. I want to find my initial velocity. I know this is always negative 9.8, and I know that it took 10 seconds to get up to the top. So if you go through and you do this math, we find out that our initial velocity is 98 meters per second. And that's going to be positive because it's going upward. And now from here, I can put this up here. And then I can use this equation. Delta y is initial velocity times time plus 1/2 gt squared. Just plug in your numbers here. We want to solve for our displacement in the y direction because I want my maximum height. And I know that that's now 98. It took 10 seconds plus 1/2. We know that's always negative 9.8. And we knew that that's 10 seconds squared. So if you run through and put this in your calculator, you will find out that this bullet or cannonball or whatnot is going to reach a height of 490 meters. It's a long way to go. Okay? Hopefully you're still with me, getting all this good stuff in your notebook. Now this one's a little bit different. It's same kind of idea as a cliff, so just remind yourself that you get up is positive, down is negative, and the one thing that's different is that we're actually giving it an initial velocity, and we want to know what is its velocity 2 seconds later. So we define our up and down, and then we get initial velocity, final velocity, displacement, acceleration is always negative little g, negative 9.8 meters per second squared, and time. Okay. So we give it an initial velocity of 10 meters per second. 10 meters per second. Be careful. This is where it's very easy to get confused. We throw it down, so that initial velocity actually is negative. Remember, that tells you the direction it's moving. We want to know what is its velocity 2 seconds later, so we just fill in all of that good information. So the trick to this is making sure you're getting your vectors and your directions correct. Remember that acceleration is always down, that's always negative. If you throw something down, that means it's a negative initial velocity. Alright, so we'll pick our nice easy one. Final velocity is initial velocity plus gt. So plug everything in. That's a negative 10 plus negative 9.8 times 2. And if you put that in your calculator, we're going to see that it is negative 10 minus 19.6. Our final velocity is negative 29.6 meters per second. Now, that negative again is just saying that it's moving downward. All right, just 2 more to go. So here we have a pirate forces a captured sailor to walk the plank from which he falls into the sea 7 meters below. How long is the sailor in the air? So we want to find time. And then with what speed will he enter the water? We also want to find final velocity. This is one where it's going to be really easy to confuse unless you draw a little diagram. Remember, up is positive, down is negative. So he's going to start here at the plank and he's going to move down to the sea. And we know that he's moving downward, so our delta y is negative 7 meters. He's walking right off the plank, so his initial velocity is going to be 0. It's not like they threw him down. And then his final velocity we're looking for, and it's right before he hits the water. So, once you get a grasp on what you're doing, make a little sketch. We just write down our variables. That one's not going to change, so we just write him in right away. Alright, my initial velocity we just set on our diagram is 0. We're looking for this. We also know that the displacement of that pirate is down 7 meters below where he started. And then we also want to find time. Okay, so it doesn't matter which variable you find first, but I'll give you a little hint that it's easier to find VF and then use it for time. So what we're going to do is we're going to do VF squared equals initial velocity squared plus 2a delta y. 2g delta y. Okay, so my final velocity I'm going to find. My initial was 0, so that's good. And then plus 2 times negative 9.8 times negative 7. So those are 2 negatives that kids get confused with and sometimes leave out by accident. So just try to make sure that you are real careful with your signs. So VF squared is going to be 137.2. So now we have to take the square root of both sides. Now remember, like we did before, it's plus or minus 11.7 meters per second. Think to yourself, which direction is he moving? He's moving down. So my actual answer for my VF, my final velocity right before he hits the water, is going to be a negative 11.7 meters per second. And then you can use this up here for your final velocity, and then you can go on to find time. The easiest way to find time, use our nice easy equation. My final velocity is my initial velocity plus my acceleration times my time. And my final velocity was negative 11.7 equals 0 plus a negative 9.8 meters per second squared times time. And then if you just divide those two, you will get a time equal to 1.2 seconds. That's how long it took the pirate to fall from the plank down to the sea. All right, so we are now on our last type of problem. Now, this one, it says that there's a helicopter. It's climbing at 8 meters per second, so we're going to assume that it's straight upward. And then he's going to drop a package to someone below. and it says that it reaches the ground. Sorry, that's a typo. I just saw it. The ground 4 seconds after being dropped. How high was the helicopter when it dropped the package? So that's a lot of information. A diagram here is going to be really helpful. You got to think that the package is inside the helicopter, so it's moving at the same speed that the helicopter is when it first is dropped. So my initial velocity here is actually positive because it's actually moving upward, and then it's getting dropped. So it's going to move downward. So this is really important to make sure that you go ahead and you write positive and negative here, just to keep track of everything, because we know that my final velocity is going to be negative, my displacement is going to be negative, and then they're asking how high was the helicopter. So we'll put this all together, and we will start with just our basics. We're going to say my initial velocity, and then we just list final velocity, my delta y for the package. Acceleration is always negative little g, which is negative 9.8 meters per second squared. And the time they tell us is 4 seconds. So my initial velocity is going to be the same as the helicopter. It's going to be a positive 8 meters per second. And we want to find change in y, or displacement in the y direction. So let's choose our equation. We're going to choose delta y, or displacement, is initial velocity times time plus 1/2 gt squared. So I put in an 8 times a 4 plus 1/2 negative 9.8 4 squared. And if you crunch out all those numbers, put them in your calculator, you will get a negative 46.4 meters. It's negative because the package actually traveled downward. The package is now below where it started. So negative for the package. But what's the question actually asking you? It's asking you how high the helicopter was when it dropped the package. So if the package went down negative 46.4, the actual answer to the problem is that the helicopter was 46.4 meters above the ground. Okay, so I hope that you went through and you wrote these examples down, and you have them on video so you can always go back and listen to the explanations. Biggest things are that the acceleration due to gravity is 9.8 meters per second, and when we're on Earth in this class, we're going to always take it down as negative, so you can automatically put this in your list. Keep your vectors straight. Remember, displacement, velocity, they both have direction. So if something's moving up, the velocity is positive. If it's moving down, the velocity is negative. If it moves to a higher point, then delta y is positive. If it is now below where it started, then delta y is negative. Keep all of those things straight. The more organized you are, the easier time you're going to have. So you have that Mastering Physics assignment. I want you to get that done, and good luck. Thank you for watching.